Okay, this will be the last part of Module 5, the Dimensional Measurement Statistics tutorial. On this problem, we're going to focus on repeated tests and pooled data. Specifically, we're looking at the question for the conveyor bracket measurement L3, compute the pooled mean, pooled variance, pooled standard deviation, pooled standard error, and mean square value using data from 6 sections, which are sections 10, 20, 30, 11, 21, and 31, based on currently available data. And then also compute the F statistic to test the equality of the population means under the null hypothesis, and compute a T statistic to compare the equivalence of means between sections 10 and 11. Recalling, of course, that we've got 6 different sections of this class where students are taking physical data of these measured parts in class, 6 different sections, Monday, Wednesday, Friday, section 10, 20, 30 on 1 week. The next week is sections 11, 21, and 31 on Monday, Wednesday, and Friday. So the part that we're looking at is this conveyor bracket, and we're specifically looking at this measurement L3. So first, we'll take a look at some of these new statistics that are introduced here. They were also discussed briefly in the central tendency and dispersion part of the lab. So first of all, how can we improve our statistical analysis of these manufactured parts? One simple idea is to repeat our tests, and repeated tests provide separate data sets comprised of independent measurements of the same measured variable. And the data can be combined to provide a better statistical estimate of the measured variable, more so than obtained from a single sampling alone. So our data, in fact, includes measurements from 6 sections, which we consider independent repeated tests. So for this analysis, it's important that each test sample be drawn from the same population of parts. By the way, we're going to do this analysis. But how do we combine tests with different number of samples? So for instance, there might be 20 students in one section and 30 in another. How do we fairly compare and combine those? So M, we consider the repeated test number, or the number of groups or pools, in this case, of measurement variable X. So in our case, M is 6 for those different sections. Each test is denoted by subscript J, and it consists of N sub J repeated measurements. Note that the number of measurements can be different, of course. The pooled mean value, we use the bracket notation, X bar in brackets. The pooled mean value combines each sample mean weighted by the number of measurements in N sub J for each test relative to the total number of measurements. Similarly, the pooled variance combines the sample variance for each test weighted by the degree of freedom, N minus 1, or nu for that test, and the pooled standard deviation is the square root of the pooled variance. The pooled standard error, also known as the pooled standard deviation of the means, is computed by summing the ratio 1 over N sub J and taking the square root of that sum and multiplying by the pooled standard deviation. So if we look at some Excel analysis, we'll see what some of these statistics look like. We're going to do a pivot table and find that, in fact, we have 6 different sections here, and different means, standard deviation, number of samples, and the variance squared, the variance, which is the standard deviation squared, for each of those different samples. And then we have to compute several different parameters here in these spreadsheets to compute those pooled statistics. We'll go over that a bit more when we look at the spreadsheet. We're also going to look at the mean square value, and the mean square value is a statistic used to test the significance of variation between the sample means, okay, and that's denoted by bracket SX squared sub B. So what we do is we subtract each mean from the pooled mean, square that, and multiply that number by the number of samples N, sum it up for all repeated tests M, and then divide by M minus 1. S sub X squared sub B is a simple measure of the variance of the pooled means. The ratio of the mean square value to the pooled variance is a test statistic called the F statistic for confirming the equality of population means under the null hypothesis. This is a measure or a variance ratio named in honor of Sir Ronald Fisher, hence the F. So F statistics describes the ratio of explained variance to unexplained variance, or an alternative interpretation is the ratio of between group variability, the bracket S sub x squared sub b, to within group variability, bracket S sub x squared. So F is large if the variability between pools is greater. Back here. F is large if the variability between pools is greater than the variability within pools, which is unlikely to happen if the population means of the groups all have the same value. So the F statistic is used to determine if the tested data has an F distribution under the true null hypothesis. Assumptions of this test include normality, homogeneity of variance, which is called homoscedasticity, independence of errors, and random sampling. A critical F value can be found such as 5% and established such that if F is less than this critical value, then that's good. We failed to reject the null hypothesis. In other words, there's no significant difference among sample averages. The observed differences among sample averages could be reasonably caused by random chance itself. In other words, this is not a statistically significant result. The test statistic for comparing the equivalence between two mean values of a repeated test is the T statistic, also known as student's t-test, defined as the difference between the two means divided by the pooled standard deviation of those two, and then also divided by the square root of the sum of frequency ratios, 1/n. Student's t-test is a statistical test used to test whether the difference between the response of two groups is statistically significant or not, and the t-test statistic follows a student's t-norm distribution. So this is all in kind of the family of analysis of variance, or ANOVA. So here's what the spreadsheet will look like that we'll go over in a moment. Looks like when we also add in the F statistic, and we find that our F statistic is 1.09. We'll go over this in more detail in a bit. If we look at a distribution of F shown here for a given degrees of freedom, and we see the data here, F and then cumulative F, we can find a 95% threshold, or where the cumulative percentage probability gets up to 95%. Define that as a threshold of 2.5. And since our F turns out to be much smaller than that, 1.1, we have reason to say that this F is not giving us cause to assume anything unusual about this data. The student's t-test statistic is similar. This case, we're just comparing two samples, and so it can actually be related back to F. F is related to t squared. But here we compute a t statistic and we plot a t distribution. And in our case, for comparing sections 10 to 11, we have a t statistic of 0.3, which is also within a 95% criteria for our data. So let's take a look at the data a little bit more closely, and we will move this down, move this way, and we'll just go right here. So here's our data, and let's first start by looking at our original form responses. We filtered down on conveyor bracket L3, and we see that we have several sections here. So if we look at the section column, section D, we have section 10, 11, 20, 21. We have quite a few data points there. So as before, we can just use a pivot table, insert pivot table on this, and I've already gone ahead and done that. And in the pivot table, we get the following results. We compute the following results: the average for a given pool or a given section, the standard deviation, the number of samples or the count for that pool, and then the variance as well. So notice that the number of samples is different in each one: 29, 18, 27, 22, 25, and 21, a total of 142 samples. So the first thing we want to do is compute the pooled mean. And so we just calculate n times x bar. And for that, we then divide by the total number of samples, 142, and the pooled mean is then 23.65, which actually is very similar to the average of these guys. Next, we compute the pooled variance, and for that, we need to compute the degrees of freedom, which is just n-1 here, and we multiply degrees of freedom times the variance of that particular pool or that particular section. So then we sum that up. So the equation is shown here, where we're summing up nu times the variance, and then we divide that by the sum of nu sub j, 136, sum of the degrees of freedom. And the pooled variance is then 27.68. The standard deviation for the pooled standard deviation is just 5.265, which is the square root of this. To calculate the pooled standard deviation of the means, it's very similar, except we need to compute the ratio 1 over n for each of these guys, sum that up, and then to compute the pooled standard error, we take the pooled variance, and then we multiply times the square root of the sum of 1 over n, this value. And we get the pooled standard deviation of the means, or the pooled standard error, of 1.369. Okay, so those are pretty simple calculations. And then we move on to computing the F statistic. And so to compute the F statistic, first we're going to compute the mean square value before computing the F statistic. So the mean square value, which is bracket S sub x squared sub b, we compute as 1 over m-1, m is the number of pools, times the sum of n sub j, the number of samples in each pool, times the difference between the average value of each section minus the pooled average. Square that and sum it all up. And so to break that down, we first compute each mean relative to the pooled mean and square that. We compute all those, and then we compute the number of samples times that deviation squared, and we get that guy here. So we end up getting a mean square value of 30.263. It's hard to tell whether that's a big or a small value. So what we typically do is we look at the ratio of that value to the original pooled variance. And so the ratio for the F statistic is 1.09. And so that's sort of the ratio of the explained to unexplained variance, or the within to between variance is another way of explaining it. So if we look at the F statistic, we're comparing to see if this value, where it falls relative to an F distribution, which is based on Fisher's statistical model. And so this is what the F distribution looks like. It's dependent on what's called the degrees of freedom. And there's two different degrees of freedoms for computing an F distribution. One is just the number of pools, or number of sections minus 1. So that's 6 minus 1 is 5. And the other is based on the total number of samples minus the number of groups. And that's 35, because we actually had 40 parts that we could sample from in this data. So with this definition of the degrees of freedom, we can plot the F distribution. We've also got the data for that using this function fdist over here. And we can see, if we look down here, especially if we look at this version of fdist is the cumulative percent, we can see there's a point where we're going to use a 5% threshold. So when we get to 95%, we now have a value that defines the criteria for what an F is that's significant or not. So we're looking to make sure that F is less than 2.5. And in this case, our F was actually 1.1. And so we fail to reject the null hypothesis. In other words, our data is sampled from all expected or good data. So that's the F statistic. And then lastly, we can look at our T statistic. comparing just two sections. And so this is similar in concept, but we just need to compute the mean for section 10 and 11, the standard deviation, the number of samples, the variance, and then the degrees of freedom, and then degrees of freedom times the variance. So to compute the t statistic, we compute the difference between the means of each pool. We divide that by the standard variance of the pool for those two sections alone, and then also divide that by the square root of 1 over n for the first section plus 1 over n for the second section. So that gives us a standard variance for those two pools of 29.78, and then the t statistic using this equation is 0.13. We can again take a look at a t distribution, and we'll look at half of a t distribution, and we'll use a criteria of, again, 5% in one tail as our threshold for defining what's significant or not. And so our student's t was 0.3, just plotting that over here, that falls right around here, and using a 5% threshold on one tail, which is pretty conservative, is 1.7 is the criteria that we're looking at for student's t. And so essentially we're saying that these two samples are drawn from similar distributions. So that's the basics of the pooled statistics, pooled repeated tests for pooled data, and how we approach looking at solutions for this class of our analysis of variance. So that's going to conclude this module, and that also concludes all of the statistical analysis tasks for the geometric measurement tutorial for our basic manufacturing statistics module.